So today I wanted to talk a little bit about predicting biofuel costs with the end goal of displacing fossil fuels. So by now we're pretty familiar with the fact that fossil fuels are pretty damaging, and that as a society we've wanted to electrify our processes. And the end goal of that is to be able to use renewable energy sources like solar and wind to power society. The problem with that is that a lot of our cheap renewable energy sources are limited in some way. So solar can only work when the sun is shining, wind can only work when the wind is blowing, and hydro is pretty geographically limited since we require these huge water pools on either side. And so we turn to energy storage mechanisms, which usually take the form of electrochemical energy storage, which gives us the agency to choose when and where to use that energy. So this works pretty well for most applications, especially we've seen deployment of like grid scale utility electrochemical energy storage, and in some mobile applications we've also seen the adoption of electric vehicles. But energy storage or electrochemical energy storage starts to become a problem when we look at energy density. So in applications that require long distance travel like freighting, or applications that require light fuels like aviation, the energy density of electrochemical energy storage starts to become a bit of a problem. So these two applications, aviation and freighting, still need those dense hydrocarbon fuels. So when we look at energy density, and here on the vertical axis we can see energy content per unit mass, and on the horizontal axis we can see energy content per unit volume, we can see that batteries are kind of suffering in the energy density department, which is fine for those EVs and stationary energy storage applications. But for aviation and freighting, we still need those hydrocarbon fuels. And actually a lot of fossil fuels and other energy storage technologies can't even compare to the incumbent gasoline and diesel techs. So were we just screwed? Because hydrocarbon fuels are kind of what got us into this mess. And in response to that, I raise you hydrothermal liquefaction, which is what we study in the TIMCO lab. So what HTL does is we can take organic wastes like green waste, food waste, and sewage sludge, put it under really high temperature and pressure, just like how fossil fuels are made, but rather than taking millions of years, we can do it in about half an hour. And it creates this biocrude that's very analogous to fossil fuel crude. And that can be upgraded into gasoline, jet fuel, and diesel. The only difference is those waste products are pulling atmospheric CO2 out of the air rather than carbon sinks in the ground. So we can approach carbon neutrality, or at least produce much lower carbon intensity fuels. But I can already hear you asking, the fossil fuel industry is really mature and supported by these huge government subsidies. So how can we hope to deploy HTL, which is a new technology, to compete economically with these fossil fuels? And the way we can track that is through techno-economic analyses, where we basically build these economic plant designs with the end goal of trying to figure out how much our fuel would cost if we made it via HTL instead of via fossil fuels. And in the literature, we actually have a lot of examples of these TEAs, but they all follow these really specific bespoke scenarios where they're looking at a specific feedstock like algae or wood or food waste or wastewater sludge, but they're very time consuming and are hard to apply to other scenarios. They generally are built around a very specific scenario, and so if we want widespread deployment, it's going to be a little tough to generalize this. So what we've done is we've created a generalized TEA model where we determine the most sensitive variables, elucidate the relationship of those variables between them and fuel costs, and then regressed a model only using those most sensitive variables and quantified the error of that simplified model. So what we found is that feedstock cost, so how much you're paying for your feedstock, the size of your facility, and the amount of biocrude you can get out of your feedstock or your yield are the most important variables in determining your fuel costs. And so we regressed our model after elucidating those relationships into this very simplified model using just those three variables rather than the hundreds of variables that go into most TEAs. When we compare our model against 27 different published TEAs, we find that our model is only about 20% off of these really time-consuming models. So in context, let's say you're a city planner in a developing nation, and your city produces about 50 tons per day of waste, and each ton of that waste laying around causes about $100 of harm. So you send some of your waste to a buddy of yours at university who says it gets about 40% yield. So you put all that info into this equation, and with about plus minus 20% accuracy, you can estimate that your fuel would be about $3.35 per gallon of decentralized, depoliticized, low carbon intensity hydrocarbon fuel. So as I finish up here, I ask you to remember that HTL is well poised to not only renewablize those high carbon intensity long distance travel mechanisms like aviation and freighting, but it's also an excellent way to decentralize a resource that even today dominates our geopolitical climate.